A number is an integer. If you know what an integer is, all the whole numbers, zero, negative numbers. A rational number is a ratio of an integer divided by a natural number. A proper fraction is a fraction where the absolute value of the numerator is less than the denominator. An improper fraction is when the absolute value of the numerator is greater than the denominator. A mixed number is an integer plus a proper fraction. And so in fourth grade, your fourth grade teacher taught you long division. And long division is a strategy for rewriting an improper fraction as a mixed number. You take an improper fraction and you say, I don't really fully understand this the way it's written as an improper fraction, but what if I could rewrite this as a mixed number? And so to do long division, you said, okay, 1,613 divided by 7. Well, how many times does 7 go into 16? 2. When was the last time you did this? Was it fourth grade? How many times does 7 go into 21? 3? And then 7 goes into 3 0 times. And my remainder here is 3. In fact, we stop doing long division whenever the remainder is smaller than the denominator, the divisor, whatever you want to call this. And then the way I rewrite this improper fraction as a mixed number is I write the quotient, which is an integer, plus the remainder over the denominator, which is a proper fraction by that point. So again, improper fraction as a mixed number, which is an integer plus a proper fraction. Do you guys remember how to do this? Okay, we'll do one more example and then we'll move on. If you're already comfortable doing this. Then how many times does 34 go into 74? 2 times. So I get 68. 748 minus 68 is, or sorry, minus 680, I should say, is 68. How many times does 34 go into 68? 2 times. Cool. So in this case, I would write my improper fraction, 748 divided by 34, as the mixed number, which is the quotient integer plus the remainder over the original denominator, which is 0 divided by 34. And in this case, the mixed number is really just the integer, right? We just say 748 divided by 34 is equal to 22. So 22 is a factor of the numerator anytime the remainder is 0. The quotient is a factor of the numerator anytime that the remainder is 0. So these are important things to know. You can only do long division to an improper fraction. If you've got a proper fraction, it just doesn't make sense to try it. Long division stops when your remainder is less than the denominator. The remainder is not going to be 0 if the denominator is not a factor of the numerator, but the remainder is always 0 if the denominator is a factor of the numerator. So in the end, we write, of course, numerator divided by denominator is equal to quotient plus remainder over denominator. Okay, so you'll notice a really obvious analogy here. A function is a polynomial if you can express it in a certain way, right? You know what polynomials are. A rational function is a ratio of 2 polynomials, a numerator polynomial divided by a denominator polynomial. A proper rational function is just like a proper fraction, except we don't say one polynomial is bigger than the other. We compare polynomials by their degree. So a proper rational function is one where the degree of the numerator is less than the degree of the denominator. An improper rational function is one where the degree of the numerator is greater than or equal to. That's important. This is greater than or equal to the degree of the denominator for improper. And every improper rational function could be expressed in a mixed form, which is kind of like a mixed number, where the polynomial plays the role of the integer, and the proper rational function plays the role of the proper fraction, and so on. And I rewrite it so that I have numerator divided by denominator is equal to quotient plus remainder over denominator. And our strategy for doing this is going to be polynomial long division. So if I want to divide 2x cubed plus 6x squared plus 0x plus 3 divided by x plus 5. You don't have to write plus 0x, but I think it's a smart idea to always include little placeholders anytime you're missing a term in a polynomial. Otherwise, it could be easy to make a little mistake. So then you ask yourself, how many times does x go into 2x cubed? 2x squared. Cool. So 2x squared times x gives me 2x cubed. You also multiply 2x squared times 5 to get 10x squared. Put some parentheses around that, and we subtract it, just like we did before, and we get 0x cubed and negative 4x squared plus 0x plus 3. And then we ask, how many times does x go into negative 4x squared? Negative 4x. So we multiply negative 4x times x gives me negative 4x squared. Negative 4x times 5 gives me negative 20x. We put some parentheses around that and we subtract. And that cancels out to 0x squared. 0 minus negative 20 is going to be positive 20x plus 3. How many times does x go into 20x? 20. So we get 20x plus 100. And we subtract all of that to get negative 97 for my remainder. So this time, we are going to stop the polynomial long division algorithm when my remainder has a degree less than the degree of my denominator. My denominator has degree 1. My remainder has degree 0, because a number is just a degree 0 polynomial, and so we stop because 0 is less than 1. And then I can finally go on to write my rewrite my improper rational function in what I like to call the mixed form, because it looks like a mixed number, to me anyways, where it's a polynomial plus the remainder divided by the denominator. It's quotient plus remainder over denominator. And so if I were to ask you to rewrite an improper rational function in mixed form, that's what I'm talking about. I'm talking about doing polynomial long division like this. The reason we talk about this in Calculus 2, and we'll put it off maybe for a couple weeks from now when we do more integrals, but if I were trying to take the antiderivative of this rational function as it's sitting here in its improper rational function form, I don't know what to do, right? There's no quick, easy way to do an antiderivative of this. But If I were to take an antiderivative of this in green, well, it's super easy to take antiderivative power rule of each of these terms, and then this last term is an antiderivative involving a natural log, right? The antiderivative would be like negative 97 times natural log of x plus 5. So by doing polynomial long division, you can take antiderivatives of improper rational functions. That's why we talk about it in calculus too. Exercise 3. Rewrite the following improper rational function in mixed form. So same deal. We are going to quickly do the polynomial long division to this thing. Before I start, I'm going to rewrite my denominator as x squared plus 0x minus 9. And then I think, how many times does x squared go into 3x squared? That would be 3. So I multiply everything in the denominator by 3. I put parentheses around that, and I subtract. And I'm going to end up with 6x plus 30. And then I stop. Because the degree of my remainder is already less than the degree of my denominator. My remainder has a degree 1, but my denominator has degree 2 now. So I can rewrite this improper rational function as the quotient plus the remainder over the denominator. And if I were taking antiderivatives, again, I can't take the antiderivative of this thing as it's originally given to me because it's improper, right? Even though the degrees are the same, we still consider this an improper rational function. Over here, this is closer, but I still don't really know how to take the antiderivative here either. But we will discuss some strategies for doing that. Might even talk about that today. Have you guys ever done partial fraction decomposition in your pre-cal class before? Probably. Nobody? Probably? It's been a while? I saw it. Okay, we'll do partial fraction decomposition today too, but it's coming up. We'll do one more, I think. I think this is my last polynomial long division, so just hang with me for a second so we can see if there's anything new or different about this example before we move on. Oops. I'm going to go ahead and write the 0x term so I don't forget about it. All right. X squared goes into 2x cubed 2x times. So I put all that stuff in parentheses, subtract it, and let's see what we get. Negative 5x squared plus 0x minus 5. All right. Then x squared goes into negative 5x squared negative 5 times. And my remainder is zero. So I can rewrite this improper rational function as the quotient plus the remainder over the denominator. But of course the remainder is 0, so I don't even need that. Turns out that this cubic polynomial could be factored as x squared plus 1 times 2x minus 5.
I have a question.
Yep.
like write up the 2x on top? Why don't you line it up with like the other?
Oh, yeah, you can do whatever you want. You can make it line.
Like exactly where it would end, I think.
Oh, yeah.
If it's
I guess that makes sense.
Yeah.
Yeah, I'm always just looking for the degree of the remainder, and I thought, oh, the degree of the remainder is 0. That's less than 2, so I'm going to stop. But you're right. You could line it up, and that could tell you when to stop doing. It's true. It's a good way to think about it. But yeah, so when my remainder is 0, that means the denominator was a factor of the numerator all along. So these are important things to remember. You only do polynomial long division to an improper rational function. That means the degree in the numerator is greater than or equal to the degree of the denominator. Polynomial long division stops when the degree of the remainder is less than the degree of the denominator. The remainder is not 0 when the denominator is not a factor of the numerator. The remainder is 0 when the denominator is a factor of the numerator. In the end, this is the formula called the polynomial long division algorithm. We take numerator divided by denominator equals quotient plus remainder over denominator. And notice this too. We haven't talked about this yet. In every case, the degree of that quotient polynomial is going to be equal to the degree of the numerator polynomial minus the degree of the denominator polynomial. This is always true. We can verify this really quick for those last 3 examples we worked. That the degree of the quotient is the difference of the degree of the numerator minus denominator. So in this case, the numerator has degree 3. The denominator has degree 2. So the quotient should have degree 1. Sure enough, degree 1. In this case, the numerator has degree 2. The denominator has degree 2. So the quotient should have degree 0. And in this case, the numerator had degree 3. The denominator had degree 1. So the quotient should have degree 2. Perfect. Now, every rational function can be represented these 4 ways, and they're not always distinct from one another, right? But whenever the numerator polynomial and denominator polynomial are both expanded form polynomials, we call that the expanded form of a rational function. And just like we can factor polynomials, we can factor both the numerator and denominator polynomial to put it into factored form, right? That's what I call the factored form of a rational function. Also, like we just saw, I could take an expanded form improper rational function and do polynomial long division to that to put it into this mixed form, right? So this is this rational function, but after we do long division to it right here. And then there's one more thing we're going to learn about today, which is what it's often called partial fraction decomposition, where you start with an improper, no, misspoke. You start with a proper rational function. You would only do partial fraction decomposition to a proper rational function, kind of the opposite of long division. But when you decompose it, you get what I would call this decomposed form. And this is actually the same function. You can see the quotient is the same. But notice in the denominator, this x squared minus 9 factors into x plus 3, x minus 3. And we can decompose that into 2 different proper, well, I mean, I guess it's a proper rational function here to begin with, but we can decompose it even further. And so that's what we're going to do today. One thing that I think is cool, and I don't know if students really appreciate this as much as I do, but I think it's really, really cool to see that like 3x squared plus 6x plus 3 divided by x squared minus 9 is really the same function as 3 minus 2 over x plus 3 plus 8 over x minus 3. And so you plot both of them in Desmos, and you see, yeah, that red curve is exactly the same as the blue curve. It's the same function. They look wildly different in terms of the way you choose to express this, but it's still the same somehow. And I don't know. I think that's just a really cool way to check your answer. If you do these kinds of problems, and you're checking your answers on the homework, it's a good way to make sure you got the answer right. And if you don't get exactly the same curve, you go back and you try to fix it. So there's a joke, and just as a warning, this joke is not very funny, but the joke goes, a mathematician, a poet, and a philosopher walk into the faculty lounge, and they're sitting around talking to each other, killing time. And the philosopher, he's all about getting down to, like, you know, the essence of something. What's the significance of your whatever? So he says to the poet, he says, what is poetry anyways? What's the essence of poetry? And the poet thinks for a minute, and he says to the philosopher, poetry is the art of calling the same object by different names. So the philosopher goes, that was really well spoken. That was really well said. What an elegant way to talk about poetry. And the philosopher says to the mathematician, he says, what is mathematics anyways? The mathematician thinks for a second and then says, you know, mathematics, it's the, mathematics is really the art of calling the same object by different names. Because so many math problems are like this. You have the same exact object, but because I can't take an antiderivative of this, I have to call it by a different name until I can take an antiderivative of the decomposed form pretty easily. Same exact object, same exact function, but it's nice to be able to convert between the different forms. So the procedure for converting a rational function from mixed form to decomposed form is sometimes called partial fraction decomposition. Sometimes people call it the method of partial fractions, and it would mean the same thing if somebody just in context called it rational function decomposition or decomposition or whatever. But there's 4 main cases that you need to be aware of. One case is that and by the way, this is not talking about the numerator. This is only talking about the factorization of the denominator. It depends on how the denominator factors. If the denominator factors into all distinct linear factors, that's one possible case. Number 2, maybe you have repeated linear factors. Like maybe my denominator factors into something like x minus 1 times x plus 2 cube. I would call this a repeated factor because it's x plus 2 times x plus 2 times x plus 2 in the denominator. Another thing that could happen when you factor the denominator is you could come up with irreducible quadratic factors. And the word irreducible means maybe I have something in my denominator that looks like x squared plus 1. Now you and I know that I could factor x squared plus 1 as x plus I times x minus I. It could be factored into linear factors. But we call it irreducible because you can't factor it without using complex numbers. And in our case, in Calculus 2, we want to stick with real numbers when we take antiderivatives of rational functions. So we're going to treat this as a separate case, and I'll show you what to do in the case of finding an irreducible quadratic factor in the denominator, like this one, where we just want to keep our real numbers around, so we leave it as quadratic. And again, if I wanted this to be a repeated irreducible quadratic factor, that's talking about a case whenever you have something like that, but maybe it's raised to the 2 power. So that would be repeated if you have something like that. That would be the 4th case. So I'll show you one example of each case. This is what it looks like to do decomposition with distinct linear factors. So on your homework, exercise 5 says rewrite the following rational function in decomposed form. This is already a proper rational function, so there's no need to do long division, right? But what I want to do is I want to write 5x minus 7 divided by x minus 1, and then I might have to do some factoring. Like, how does x squared minus 5x plus 6 factor?
Is it x minus 3, x minus 2?
Yeah, that's right. Okay, so I factored this, and now I'll show you how to do the new part, the decomposition part.
Did we talk about this last semester?
Did we do this in Cal 1? I don't think we did this in Cal 1.
It seems familiar, but maybe not. So does it come up in statistics at all?
No, definitely not statistics, no. The stats kids would have an aneurysm if I had to do this. But this is the idea, is that I've got this rational function, and it's got these, poles of multiplicity 1, or the vertical asymptotes in the graph are simple multiplicity 1 vertical asymptotes. And so maybe I can rewrite it where I just have a constant divided by each one of these. And then if I add them together, I should still get vertical asymptotes at the same places, right? With the same multiplicity. So it seems like it could be a reasonable guess. And we're going to let capital A, capital B, and capital C just be constants. They're unknown right now, but they are unknown constants. They're not any kind of function of x. Okay, in the next step, I'll write it down and see if you understand what happened here. Kyle, what did I do here to go from the blue equation to the orange equation?
You eliminated the denominator, so you multiplied each of the terms by x minus 2, x minus 3, or x minus 1, depending on... Well, actually, you would have multiplied them all by all three and just eliminated one of the factors of the denominator by canceling out the stuff in the numerator.
Perfect. We just multiply both sides of the equation by the entire denominator on the left-hand side. So every term in the whole equation gets multiplied by x minus 1, x minus 2, and x minus 3. But some of those disappear because they cancel out with the denominator of each term on the right-hand side. Okay, so let me give you the next step in the process. Avery, what did I do to go from the orange line to the purple line?
You multiplied out the two terms in like the parentheses.
Yeah, we just expanded each term. You're right. Very good. Okay, let me show you the next step. Okay, so going from purple to green, what I've done is I said, since the left-hand side of this equation is really equivalent to the right-hand side of this equation in purple, I'm not just saying this has to be true for one value of x, we're not just trying to find the value of x, but we're actually saying that this purple function is absolutely equivalent to this other side of the equation for every value of x. And that means the constant terms have to be exactly the same. So I add up the constant terms on the right-hand side. The x terms that only contain a coefficient times x, those have to be the same. So I can add up the coefficients of x on the right-hand side. And then also the x squared terms, those have to be the same. And so I add up the coefficients on x squared on the right-hand side and set those equal to 0. So that way the left side is really equivalent to the right side only if these three linear equations with three unknown variables are satisfied by a, b, and c unknown coefficients. Now this is pretty tricky. This is pretty tough. Instead, I can think of a better way to do this. Sorry for a little bit of a I kind of went off in the wrong direction here because there's another better way to handle this. You could solve this system but there's a better way, and it's called the Heaviside method. The Heaviside method goes like this. If the left-hand side and right-hand side are really equivalent, for all values of x, then pick any three values. And they also have to be equal for any value of x, right? If they have to be equivalent for all values of x, then they will be equivalent for any values of x. And so here's what I'm thinking would be a faster, easier way versus solving a system of equations is, in the first place, choose x equals 1. And if I choose x equals 1, the left side of the equation is 5 minus 7. And the right-hand side of the equation simplifies quite a bit, because if x is equal to 1, 1 minus 1 is 0, here and here. So the right-hand side of the equation becomes a times 1 minus 2 is negative 1, and 1 minus 3 is negative 2. Negative 1 times negative 2 is positive 2. And that's it. It's pretty good.
Did you have to strategically choose a common, like a factor that's an x that's going to be cancel out two of them to get 0?
That's it. That's absolutely right. The reason I chose x equals 1 is because I saw the factor x minus 1.
But you could also have done x equals 2 or x
Perfect. That's what we'll do next.
So we'll give it a try.
What happens if I choose x equals 2? What's the left-hand side of the equation? 3. And what's the right-hand side of the equation if I choose x equals 2?
Negative b.
Yes. So I can choose, let's say, one more choice of x, and we'll observe what happens. What should my last choice for x be, Gwen? 3. And if I choose x equals 3, what does this orange equation become up here? Two C. Very good. And that tells me C equals 4. Nice. So, maybe you remember how to solve linear equations for unknown values. You use substitution, elimination, whatever the heck you want to use. You could solve this system of linear equations, but a lot of times it's a little bit faster if you use what I call the Heaviside method. I don't think it's just me that calls it that. There's a mathematician named Heaviside that this is named after. But and Heaviside's idea was if this left-hand side is really equivalent to the right-hand side for all values of x, then it should work for any values of x. And again, by looking at this factored form, I can choose strategic values of x, like 2 and 3 and 1, because that's going to zero out some of the terms. And that's how we came across this. So we just figured out that capital A is -1, capital B is -3, and capital C is 4. When I go back to this, up at the top, I can now rewrite my original function by saying A was, I already forgot, -1. So I write -1 over x minus 1, plus B was -3 over x minus 2, and C was 4 over x minus 3. That is how I can rewrite a rational function in its decomposed form. And this is what it will look like to do this procedure in the case where every factor in the denominator is a distinct linear factor. There was no repeats and there was no irreducible quadratics. So just because I love checking my answers so much, we'll show 5x minus 7 in Desmos. Divided by x minus 1 times x squared minus 5x plus 6 is really equivalent to what we found, which was -1 over x minus 1 plus -3 over x minus 2 plus 4 over x minus 3. You're right. If you get the correct answer, this should be exactly the same curve in blue and in green. And that's how you check. All right, second case. What if I have not just, ooh, that's not the right thing. That is, well, oh, it is. Sorry. Got ahead of myself. This is the second case that we were talking about. What if I have not distinct linear factors, but I have repeated linear factors? And it doesn't seem like it immediately, but what if I choose to factor the denominator? What does x squared minus 1 factor as? Yeah. So together with the x minus 1 that we're given, that gives me x minus 1 squared times x plus 1 in the denominator. And we don't factor the numerator. Just leave that numerator alone. Because what we want this eventually to look like is going to be a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. So when you have a repeated factor like the x minus 1 squared, in the decomposed form, you have to leave a term for just x minus 1 and a term for x minus 1 squared. And imagine this. What if this was x minus 1 cube? Imagine we have something over x minus 1 cube. This would require x minus 1 squared, and x minus 1 cubed. Okay, so it's every whole number up to the power of the repeated factor.
So it can go beyond C. You could have D and E.
Oh yeah.
Like go up.
What if it's x minus 1 to the 5th power? Right? You could have x minus 1 to the 4th and x minus 1 to the 5th. Yeah. But that's the idea, is you take all of the powers from 1, 2, 3, and so on up to the power of your repeated factor. In this case, though, in red, we just have the 2 factors, we only need that. Okay, so just like before, I'm going to proceed and rewrite this as 3x squared minus 4x plus 3. And on the right-hand side, I'm multiplying everything by the denominator, and so I get a times x minus 1 times x plus 1 plus b times x plus 1 plus c times x minus 1 squared. No. Okay. The heavy side trick, let's see if it works. Choose x equals what? 1. I like the idea of 1. If I choose x equals 1, then this goes to 0 and that goes to 0, and I should be left with only b. That sounds like a good idea. So we choose x equals 1, and my left-hand side becomes 3 minus 4 plus 3. My right side becomes 2b. Cool. So there's not another very, very, very strategic choice of x, but what's another value of x? It doesn't have to be perfect. What? This isn't going to be a fantastic choice, but I could choose x equals negative 1 and see what happens. Like if x is negative 1, this would be 3 plus 4 plus 3, which is 10. And if it's negative 1, never mind, that is a pretty good choice, isn't it? Because that's c times 4. Okay, now we're out of good choices. now we're at a point where there's really nothing else I can completely eliminate to just get a by itself. But even in the absence of amazing choices, you could still make a choice. Like I think x equals 0 works out decently well. Like if x is equal to 0, this is negative a plus b plus c. And I know what b and c are. So that's 3 minus 3.5. So it's like negative half. So I think a is equal to a half. Is that what you guys got? And so again, that didn't simplify as nicely, but still pretty good. Still all right. My final answer is going to be 1/2 over x minus 1 plus 1 over x minus 1 squared plus 5/2 over x plus 1. And that is the decomposed form. And again, imagine what's the real purpose of this in Calculus 2. I don't know how to take an antiderivative of this big, ugly thing, but I do know how to take an antiderivative of each of these terms. So I can do antiderivatives more easily once I accept.
How would you get it back into the original form? Just finding a common denominator?
Mm-hmm. Yeah. Yep. All right, that was the first two cases. We did distinct linear factors, we did repeated linear factors. Let's do irreducible quadratic factors, because you do handle it, this case, differently than the previous two. This time I've got 4x squared minus 3x plus 10 divided by x minus 2 times x squared plus 6. So this is what we call the irreducible one. Because you could factor this as two linear factors, but then your roots would be complex numbers. Or imaginary numbers in this case. But we want to keep all of our numbers real numbers when we do partial fraction decomposition. And so we're calling this an irreducible quadratic factor. And here's how you write the decomposed form. This is the wild new part, is if you've got to handle one of these irreducible quadratics in the denominator, you can't just write b, the constant, in the numerator. You have to write a little linear form. You've got to write bx plus c in the numerator. So it's the same game as before. We multiply both sides by the denominator. And I'm going to get a times x squared plus 6 plus bx plus c times x minus 2. And our friend Heaviside would say, let's choose x equals what? 2. And if we choose x equals 2, this becomes I think that. All right, and that's the extent of the what we're going to get out of the Heaviside method. To continue, take this equation again, and we're going to plug in a is equal to 2. So if a is equal to 2, the right-hand side has 2x squared. And I could subtract 2x squared from both sides and write this as 2x squared minus 3x. And then the right-hand side, if a is 2, will have 2 times 6, so it'll have a 12. Let me subtract 12 from both sides. 10 minus 12 is negative 2. And I've already subtracted away this a stuff. So this is going to be equal to the bx plus c times x minus 2. And I'm going to expand that. And we'll get bx squared plus cx minus 2bx minus 2c. And when I look at that equation, I think it makes it a lot easier for me to tell what is b and what is c, doesn't it? B has to be the coefficient on x squared, and c has to be so that negative 2 is equal to negative 2c. So that's how I find my b and c, by just comparing the coefficients on the left side and the right side. All right, that's it. We go back, we plug in our stuff, we get our answer. The decomposed form this time is going to be 2 divided by x minus 2 plus 2x plus 1 over x squared plus 6. And if, again, I'm thinking about the application here, on the left side, I don't know how to find an antiderivative of that original purple rational function. And our answer, I do know how to take the antiderivative of this first term. That would be 2 natural log of x minus 2. The second term, we don't know how to take this antiderivative yet, but we will. We'll learn strategies for taking that antiderivative. It's just going to be here in 2 or 3 weeks that we get around to talking about that. But this is the first step. Okay, our last case, our fourth case of what it could look like to do partial fraction decomposition. And when I look at this, I'm looking at 2x cubed plus 3x divided by x squared plus 1 squared. So this is when I have a repeated irreducible quadratic factor. And we're going to have to make this very ugly. Because when I have a quadratic factor like x squared plus 1, the numerator can't just be a constant a, it's got to be a linear form, ax plus b. Then, because it's repeated, I also have to throw in x squared plus 1 squared. And again, I've got to put a linear form in the numerator. So that's what we end up with. Just like before, we're going to multiply both sides by the denominator, and we see what we get after we multiply both sides by that denominator. I'm going to expand everything. This time I'm just going to go straight for expanding things. Like 2x cubed plus 0x squared plus 3x plus 0 is equal to ax cubed plus bx squared plus a plus c x plus b plus d. So I've got things lined up into the x cubed coefficients, the x squared coefficients, the x coefficients, and the constants. And again, we can convert this into a system of linear equations just by comparing the coefficients. Like 2 is equal to a, 0 is equal to b. 3 is equal to a plus c, and 0 is equal to b plus d. So a is equal to 2, that's obvious. Also b is equal to 0, it's kind of nice. That means c is equal to what, and d is equal to what? 1 and 0. 2, 0, 1, 0. So to write your answer, 2x over x squared plus 1 plus x over x squared plus 1 squared.